We concede that we will never have all of the data on all the observations of a population, unless it is a trivial problem with only a few observations. Once we concede this, we are left with sampling to find the insight into understanding the population data. So we draw a sample. We are careful. We draw the sample randomly. But which sample did we get? There are theoretically an almost infinite number of samples. With just 100 items in the population, there are more than 75 million samples of size 5 that can be drawn. If 6 are in the sample, the number of possible samples increases to just over 1 billion. So, of the 75 million then, which one did we get? If there is variation in the items to be sampled, there will be variation in the samples. One could draw an unlucky sample and make very wrong-headed conclusions about the population. This is a true insight. Any sample we draw is really only one of a distribution of samples. From this comes what is probably the single most important theorem in statistics, the central limit theorem. Without the central limit theorem, it would be impossible to proceed to true statistics from simple probability theory. In its most basic form, the central limit theorem states that regardless of the underlying population density function, the theoretical distribution of the sample means from that population will be normally distributed. In essence, this says that the mean of a sample should be treated like an observation drawn from a normal distribution. The central limit theorem only holds if the sample size is large enough, which has been shown to be about 30 observations or more. This figure graphically displays this very important proposition. Okay. Here is our population. Okay. And maybe it looks something like that. Okay. It's a continuous random variable, and these are the x's. Okay. Down here are x bars. This is a theoretical distribution of sample means taken from that population. Let's say that this is the mean of that population. Down here, we have the normal distribution. So what we have here is the mean of the x bars. We're going to call that mu sub x bar. Then we have sigma sub x bar, which is the standard deviation of this distribution. Okay? So what we're looking at is this thing here. I've drawn this all squiggly to show that it does not matter how oddball this really is. It doesn't matter, period, what that is. Okay? Remember, we will never know what that distribution looks like anyway. The horizontal axis is labeled x's. Now, this is the theoretical distribution called the sampling distribution of all the mean values of all the possible samples that could have been taken from the population. Of course, no one would ever actually take all of these samples, but if they did, this is how they would look. And the central limit theorem says that they would look normally distributed. The central limit theorem goes even further and tells us the mean and standard deviation of the theoretical distribution. The best way to capture this information is to build a table. And so what I have here is the parameter. And we have two parameters we're interested in. Okay? We have the mean and the standard deviation. Now, over here, we have the population. Okay? Here's the population. This is up here. The population has a mean unknown to us. Okay? It has a standard deviation, also unknown to us. We're using the Greek letters here. Okay? Now, if we draw a sample, a single sample, that single sample will have a mean called x bar. So there's x bar. It will also have a standard deviation called S. This distribution here, called the sampling distribution, it has a mean, the mean of the means, if you will, and it has a standard deviation, sigma sub x bar. The practical significance of the central limit theorem is that now we can compute probabilities for drawing a sample mean in just the same way as we did for drawing a specific observation of x's if we knew the distribution was normal. The standardizing formula has to be amended to recognize this. If we're moving from here, and it's a normal distribution, then we had our standardizing formula. And you'll remember that it is z equals x minus mu over sigma. But we're not doing that. We're moving from a distribution that has a mean, mu sub x bar, and we're not going from an x, we're using x bar, and this has a standard deviation, sigma sub x bar. So what we have here then is a standardizing formula that will move us from the sampling distribution. Okay? Now, an important information. The expected value of mu x bar is equal to the mean. I've purposely drawn the population mean, which is unknown to us, the population mean directly above the mean of the sampling distribution. This theorem adds this piece of information. The expected value of this guy is equal to what we're actually after. Okay? Notice the similarity in these two formulas as you see these as they go. Okay? This one is simply x minus mu over sigma if we know its population. They both say the same thing. How far in standard deviations is the mean from a particular x value that I'm interested in? Only in the first case, up here, the x is a particular observation, okay, in the population. And in the second case, here, it is the sample mean, x bar. And we are interested in how far this is from the true population mean mu. This is how we're going to turn statistics problems into probability problems. We now see that the sample mean is really just an observation from a normal distribution, and we know the mean and standard deviation of that distribution. And for all this, we thank the central limit theorem.